everyone, so today we are going to be talking about acid-base chemistry. So first let's start off with talking about Arrhenius acids and bases. So Arrhenius classifies that a substance is an acid if it creates hydronium ions in water. So when we have an acid-base complex, we have hydrogen ions and we also have hydroxide ions, and that creates water. So as you can see in this diagram, here's the hydrogen atoms or ions and the hydroxide ions, and they create water. But Arrhenius says that a substance that has many H plus ions is going to be very acidic, whereas a substance that has many hydroxide ions is going to be very basic. So as we can see over here, HCl, that's a common acid. It's an acid obviously because it has many H ions. And then NaOH, it's a common base. It's basic because of the hydroxide ions. And Arrhenius states that in addition to complete dissociation in water, so this is assuming strong acids and bases, the product is also going to be a salt. So if I were to combine hydrochloric acid and also sodium hydroxide, I would get sodium chloride, which is a salt. Okay, and then there's also another theory, and this is called the Bronsted Lowry theory of acid and bases. So instead of assuming a complete dissociation in water, Bronsted Lowry takes in for the account that not everything dissolves completely in water, especially things like acetic acid, which is a very weak acid that only partially dissociates in water. So in a Bronsted Lowry system, there are proton donors and proton acceptors. So the hydrogen ions are the proton donors. Whoops. Are the proton donors? No. Okay. So the hydrogen ions are the proton donors. And the hydroxide ions are the proton acceptors. And there's a conjugate acid-base pair. So let's look at a Bronsted Lowry acid-base reaction. So what if we had, let's see, hydrochloric acid, and then if we added ammonia, and then we created the ammonium ion, and then also chloride ion. So let's see. So when you have a conjugate acid-base pair, the conjugate acid is always going to have one more H than the conjugate base. So if we look here, it's evident that this is a conjugate acid of Cl because it has one more H than the Cl ion does. So this is a conjugate acid-base pair in which HCl is the acid and Cl is the conjugate base. Now I know that doesn't seem, well, it seems a little strange because Cl is not normally a base, but in this system, it's a conjugate base of HCl. And then also here we have ammonia, which is NH3, and also the ammonium ion, which is NH4+. So here we can see that NH4+ is going to be the acid because it has one more base than ammonia, and the NH3 is going to be the base. Okay, so let's look at a practice problem here. So I'm going to have you find the conjugate acid-base pairs in the following reaction, just a hint, there's two, of sulfuric acid and water. So if you just pause the video and work on that for a second. Okay, let's see how you did. Okay, so here we have the sulfuric acid and the water, and it's creating a bisulfate ion and a hydronium ion. So we obviously know that sulfuric acid is going to be a conjugate acid because it has two H's compared to the bisulfate's one H. So because it has one more H than the bisulfate ion, we know that this is going to be a conjugate base of the sulfuric acid. Now let's look at water. Now I know that water isn't normally considered a Bronsted Lowry base, but in this scenario it is because look at the hydronium ion. The hydronium ion has one more H than the water, and the hydronium ion is just another way of saying the H+ ion. So anytime an acid combines with water, it's going to create its conjugate base and also excess hydronium ions, or H+. Okay, So now that we've discussed the different types of Bronsted Lowry acids and bases and also Arrhenius, let's just talk about the pH scale in general. So the pH scale ranges from 0 to 14, but really 1 to 14 when we're talking about the actual scale. So acids are less than 7, and bases are greater than 7. So acids are in this range, so 1 to 6 really, or 1 to 6, 7. And then neutral is considered pure water. And then bases are very alkaline, and they're going to be all the way over here. So from 8 to 14. Some common acids we have battery acid, gastric acid. Also lemon is a common acid, and it's a pH about 2. Hydrochloric acid, soda acid rain. So it really puts in perspective the different kind of acids and how strong they are. Of course, we all know that hydrochloric acid is a very strong acid. And then also pure water with a pH of 7. And then you start getting more basic seawater, slightly more basic, and then baking soda, magnesium, ammonia, which we saw in our Bronsted Lowry acid-base complex, Sepoy water, bleach, and drain cleaner. So to find a pH value, you take the negative logarithm of the H plus value. So the H plus value is basically the concentration of the hydronium ions. So the negative log of the H plus will give you the pH, but then if you want to find the pOH, it's a little bit different. The pOH is basically the concentration of the OH ions, and you can, if you only are given the concentration of the OH ion, so if you say sodium hydroxide has a pH of 5.6 times 10 to the negative 6 or something like that, you can use a pOH to find the pH, because we don't really use pOH, we usually only use pH. So to find the pOH, you take the negative log of the OH value, and then your pH plus your pOH is going to be equal to 14. So when you find your pOH, so your pOH is 6, then you know that your pH must be 8 in order to equal 14. Okay, so when doing anything with acids and bases, it's always important to know your strong acids and strong bases. So let's look at the strong acids. So here we have hydrochloric acid, hydriodic acid, and also hydrobromic acid. These are all halogens, this one, and this one. But we also need to note that fluorine is not on here. Fluorine is very electronegative, and it creates stronger bonds, which makes it harder for it to completely dissociate in water. So we do consider the halogens very strong acids. However, hydrofluoric acid is not a strong acid. So the strong acids are going to be hydriodic acid, hydrochloric acid, hydrobromic acid, and then some other ones you might just need to memorize are, whoops, I forgot the coefficient on that one, but HNO3, nitric acid, perchloric acid, and also sulfuric acid. And then in terms of the strong bases, a strong base is all alkali metals that are combined with hydroxide. So anytime you have something like KOH or NaOH or even CCMOH, you don't really see that often, but these are all going to be very strong bases that completely dissociate in water. Some other ones you may see are strontium hydroxide. That's an alkaline earth metal, and it's a pretty strong base, but it's not going to be as strong as some of your bases that are combined with the alkali metals. Okay, so let's look at a titration practice problem. So a titration problem involves an acid and a base, and you're combining them to form water and a salt. So this is kind of similar to that Arrhenius idea when you have a really strong acid and a strong base, and you're getting water and a salt. So the problem says that we have 50 milliliters of 0.5 m barium hydroxide are needed to fully titrate a 100 milliliter solution of sulfuric acid. So what is the initial concentration of the acid? Okay, so let's see here. So we have 50 milliliters and we have a 0.5 molar solution. And we also know that we have 100 milliliters of this. So in order to solve this problem, we're going to use molarity equals moles over liters. So it's also important to know this formula because this is a basic stoichiometry problem. So in stoichiometry, we can use our molarity formula, our gas laws formula, our mole to gram conversions in order to figure out what units to use and how to convert things in order to be able to use moles to use the proper ratios. So let's go ahead and set this up as molarity. So we have 0.5 m is equal to x over 0.05 because we want to put that in liters. So when we do that, we get that there is 0.025 moles of barium hydroxide. Now let's find what we're looking for. So we want to find the initial concentration of the acid. So which one's the acid? Well, we know it's this one, sulfuric acid. Okay, so now we have 0.025 moles, and I already balanced the equation for you, but you know that, 0.025 moles. So there's 1 mole for 1 mole, so because it's the same ratio, it's 1 mole of barium hydroxide for every 1 mole. So there is going to be 0.025 moles of hydrosulfuric acid. So now what we're going to do is we're going to plug this back into the molarity formula so we can find the initial concentration. So we're going to have, so we're trying to find the molarities, that's what we don't know. And then we have 0.025 moles over the total liters, which I'm going to change to 0.100. And when we find that, you simply divide, and we find that the concentration, a good way to write the concentration is a square bracket, and then the H2SO4 is equal to 0.25 m. Okay, well, thanks so much for watching. I hope you enjoyed the video and be looking for another video soon.